Hey, good evening, everyone. So today we'll be doing section 7.8. This is on improper integrals. There's two types of improper integrals. One that's easy to spot is when one of the limits of integration, or it could be both, has an infinity symbol. So maybe something like this, 1 over x equals 3 dx. But this is one type of improper integral. So you just, one of the limits of integration is empty. And it can be both. It only have to be one. You can have a negative thing down here. So that's one type of improper integral. All right. The other type won't have an infinity in there, but maybe it has a 3 and a 2 and a 5 over x minus 2 dx. This is another type of improper integral. Do you see what's going on here? Right here, at x equal to 2, what would happen to this rational expression?
0.
Yep, 0 in the denominator makes it undefined. So this is causing what we call, the infinite discontinuity at x equal to 2. And so these are the two types. So now we got to look out, in this section. If you don't see any infinity symbols on there, and negative infinity and positive infinity, you're working the integral. Just check to see, well, maybe one of these limits of integration, or it could be a number between these two where the expression's undefined, right? Just to give you another example. This could have been like, we went from 2 to 4, but then this was x minus 3. Well, x equals 3 makes this expression undefined, true? And between 2 and 4 is x equals 3. So that's the other type of improper integral we're dealing with. You'll notice most of them do have the infinities on the limits of integration. So I'll get started. We'll look at these two cases right here. 1 over x dx. And then we're going to get 1 over infinity, 1 over x squared dx. I mean, by far, this is the best example to start with. We'll do both of these problems. And what we're doing is, now when integrals find the area underneath the curve, between that curve and the x-axis. So if this is going towards infinity, what did x equal to 1? Do that here too. And at x equal to 1, these graphs will find the area from 1 towards what? Infinity, like this. I'll just keep going forever. Let me just get started. I'm wondering, is this going to be, when we're trying to determine that area, is it finite or is it infinite?
Infinite.
Yeah, that's what we're looking at. Is that infinite or is that finite? Same thing here. So this thing comes like this, and it goes like this, keeps going down. Although this gets down a little bit lower, just because that's the x squared. But still, we're wondering these areas here. Because integrals do deal with area. Is the area infinite or is it finite? Does it actually converge to a value? So that's what we're looking at. So to do this, we use limits. But in the end, we're going to figure out, is this area or this area a finite area or an infinite area? All right, we'll discover it by playing around with this. We'll do this with every problem. I'll write limit as t approaches this number, because that's where the problem is, right? For the improper integral. I'll write limit as t goes to infinity, and then replace the infinity with a t. And everything else stays the same. So it's a limit problem. This is a limit problem. That area, right? Is it converging or is it diverging? Convergent meaning convergent to some finite value, like 3 or 3/2, 1.7. All right. So we'll do this one, then we'll work this one. What's the integral of 1 over x? Natural log x. I'll put the bars. So we'll go from 1 to t. I'll write this again. Then this t goes to infinity. And now I'm going to substitute a t in here. And then I'll substitute a 1 in there. And each one of these, we'll figure out what's the limit as t goes to infinity. All right? So when I substitute a t into the x, this becomes now natural log of t. Is everyone okay with that? I know, that's what's going to happen because we replace the infinity with this t value, or this t variable. I'll plug the t in there and go, all right, well, I get the natural log of t minus, and then I plug in natural log 1. What we're going to do is, still in front of both of these, I have this limit as t goes to infinity. And yeah, you can write that lim t goes to infinity, lim as t goes to approaches infinity. This is a limit. The limit as t approaches infinity of the natural log of t. I'm taking the bars off everyone right now because this isn't going towards negative infinity. Does that make sense? And it's a limit problem, so I'm going to remove those bars so they don't bug you. Because it's not going towards negative infinity or anything. I'll put minus, and I'll do the limit as t approaches infinity of this number. What is the natural log of 1? 0. I'll still put it. Nothing crazy here, everyone. What's the limit as t goes infinity of a 0? 0. Hey, by the way, what if this was like an 8? The limit as t goes infinity of 8 would be 8. 8 is a constant, it's just a flat line. So it always stays 8. So whatever constant you get in these problems, you get a constant with any variable. Limit as t goes to infinity of 19. Now, to answer this final question, we want to know, does this integral converge or diverge? It comes down to this. The limit as t approaches infinity of natural log of t. So we need knowledge of that function. What's the natural log function do? You can look at limits algebraically sometimes. You can look at limits graphically. There's still L'Hopital's rule, remember that? But I say we have knowledge of the natural log graph. The natural log graph, y equal to natural log of 2. Has a vertical axis up here, but what's it do as t approaches infinity? It slowly keeps rising. I mean, it may rise very slowly, but it keeps rising forever. So where's this headed? This is infinity. Does everyone agree? The natural log of t, the limit as t approaches infinity, we're just like, what's happening to this y value? Although it's rising slowly, it's heading towards infinity. So now we know the answer, Owen. What's infinity subtract 0? Infinity, and so for answer, we're saying, what's going on with this integral? This integral diverges. Now, if you want to write diverges to infinity, you can. So we were talking about area. Can you tell me about the area? What was that area I was talking about before? It's infinite. There's infinite area there. Here, I'll draw a picture again. You go, how much area is in here? There's infinite area from, what, we started at 1? 1 over x, and this is this function right here. And it's infinite area. So if you get infinity, hey, what if you got infinity minus 1,000? It'd still be infinity. What if you got infinity plus 100,000? It's still infinity. What if you get infinity minus 100,000? It's still going to be infinity, meaning the integral what? Diverges. For it to converge to a number, somehow when we do the limit, that infinity is going to have to disappear, right? All right. So now we'll look at this problem. Side by side, we're going to leave that up there. Let's do that integral. And this has happened too many times on a test, so be careful. Does that look right? No. No, good. So put a big X to that in your note. Go, I'm not going to do that on a test. It happens often. It looks like this, right? The antiderivative whenever x is natural log of x. But this looks just like it. And you know, I guess that's natural log of x. No, we're going to perform that by thinking of that as what?
U sub?
Well, we won't even need a u sub, but we'll think of this x to the second in the denominator as just a
X to negative.
x to negative 2. Very good. And we'll approach the problem. Let's see what comes out of this. So I'll start, same setup. I'll write limit t approaches infinity. We'll do that every time. Unless there's one of those discontinuities that are like a 2. We'll deal with one of those later. I'm going to write limit t approaches infinity of this expression right here. I place the infinity with that t, everything stays the same. And I just keep writing this throughout the whole problem. Limit as t goes infinity. Limit as t approaches infinity. Limit as t approaches infinity. What's that antiderivative? Pump it up by 1. Does it become -3 or -1? Good. If you increase -2 by 1, you get x to -1. Then you can divide by the number, right? Okay, there's the antiderivative. We don't have to put the plus c because we're going to evaluate this limit. Okay, cool. Let me put my 1 to t. Before we plug in t, and before we plug in 1, can we clean that up? This goes back to the denominator as x to the first. And the -1 makes it stay negative, right? I'm just going to rewrite that. Just so it's nice and we could say clean or pretty. Looks a little weird there. I'm going to write this as -1 over just an x, because that came down here. It's still negative because that -1. And look at this. Okay, so we're getting, what's the limit? As t approaches infinity of substitute a t for x. That. Subtraction, and then do the limit as t approaches infinity of -1 over 1. And we'll see whether this diverges or converges. The last one diverges, this looks just like it. Can we start with the easy one? This is the easy part. When you get limits t approaches infinity of a constant, you just get that constant. So let's limit as t approaches infinity of this flat line, y equals -1.
-1.
-1. And what's a minus a -1?
Other plus.
So I'm going to put +1 here, just so one sees that. Again, I got minus, this is just -1. Minus, -1, +1. So it always comes down to this one part here like it did before. We need knowledge of that. Now, you could look at this limit a few ways. I did graphically. You could look at the graph. You might have the graph in your head. You might know exactly what that graph's doing. -1 over t as t approaches infinity. Some students like to do it numerically to figure out what this limit is. So let's try this numerically since the last time I used a graph. You ready? T goes towards infinity. Let's think of some really big numbers. -1 over 100. -1 over 1,000. -1 over 1,000,000, -1 over 1,000,000,000,000. Those numbers keep getting smaller and smaller and smaller and smaller. Where's this going? 0. Guess what, everyone? No infinity there. This integral converges, and what value does it converge to? 1. It converges to 1. We're saying finite area. So I'm going to put that down. There's a finite area here. And that's why it's a great way to start this section. My goodness, these look the same. I mean, if you want a cell phone shop, well, this is in the book too. You know, every calc book should start with this example. Just because they almost look the same. This one's diverging, this one's converging, right? And heck, you can see a pattern to this. You might start studying a pattern. Okay, x squared converged, x to the first diverged, and you're like, maybe I can figure out a pattern to what that power of x has to be for it to converge, right? Seriously, it's something you can just start thinking about. Is everyone okay with this? So this converges to 1. You can just leave your answer as 1. The directions to all these problems, and I'll write this on the board, but this is what they ask. Sorry. For the problems for the remaining, we'll do a bunch of these together today. There you go. Determine whether each integral is convergent or divergent. Evaluate those that are convergent. And I'll write that on the board. Hey, the first couple problems in your homework that I put for practice were just problems for you to go, you know, which type of improper integral was it? If you see an infinity symbol, it just means it's got the limit of integration is infinity.
Professor Messer, I have a question about this limit here. Isn't it going farther and farther away from 0? Because if you choose a really big number, let's say 10,000, -1 divided by 10,000 is -10,000. Isn't that going farther? I'm looking on the number line. Isn't that going farther away from 0?
So we're thinking of these numbers. You can think of them as dots and what value it's approaching. So you're right. You're like, I'll make a number line here too, because you're thinking number line. Like here's 0. Let's start with like, you want to use a half? -1 divided by a half would be 2, right? I'll use dots. Okay, we're here. Now let's go higher. So I used a half for t. Let's use 1. -1 over 1 is 1. -1. Oh, and by the way, they're negative, so I'll get on this side. I apologize. I just realized that. So let me start again. I use t equal to 1/2. It gives me the value -2. And then I go to a higher number. I went to what? T equals 1. It's now at what? -1. So it went from here. The dot was here. Now the dot's here. And then let's bump it up. Let's go to 10. -1 over what? 10. -1/10 is about right there. And then we use -1 over 100. That's about here. -1 over 1,000. That's about here. But you see what number it's closing in on?
Oh.
It's approaching. It's getting closer and closer to 0. And I did that numerically. Can we look at this graphically? What is the graph of y equal to 1 over x? Look, there's an natural log of x. Well, what is y equal to? This is what? This would be y equal to 1 over x. That's what the graph looks like. But it had a negative, right? So I'm going to rewrite this as -1 over x. You know what that graph looks like? It just looks like this. And this is y equal to -1 over x. But you see it heading towards the horace? Remember horasses? It's heading towards this horizontal asymptote, the y value 0. There's a piece over here, but we didn't care about this piece, did we? This is up here like this. Yeah, that's towards negative. Cool. Hey, you agree all expressions like this, 1 over x, 1 over x squared, 1 over x cubed, all these right here, as x approaches infinity, these are all going towards 0, aren't they? Yeah, they're those rational expressions that have a horizontal asymptote. The horace, all these. They're heading towards, as x goes towards infinity, these are all going towards 0. Cool. All right. Well, we looked at those graphically. We got these. Finite. This is infinite area diverges. Hey, I want to put those directions on the board. And we'll just leave it up all class. Do a few of these problems together. All right. I'd like to do one just like that, because maybe you'll start stumbling upon a pattern with this. The direction, determine whether each integral is convergent or divergent. So we did our warm-up. Those were 2 neat examples. So if it's divergent, you can write your answer as divergent. That's when you get those infinities. But if it converges, they wrote this for the next sentence. Evaluate those that are convergent. That means we'll put down the actual value, that finite value. It might be irrational, but these are improper intervals. So, all right, try this. How about 1 to infinity? 1 over the cube root of x. I wanted to do this next because it's like the last 2. I mean, this top number doesn't have to be a 1, it could be 100, it could be a 10, it could be a 7, but the one had a denominator of x, the one that had the denominator of x squared, which one converged again?
It was 1 over
1 over x squared ended up converging. The 1 over x ended up diverging. And now we got 1 over the cube root of x. But this is not a natural log antiderivative, right? This is like working out the x to the -2 we had last time. I can write that as x to the
-1/3, -1/3.
I love it. So I'll put that first before I write my limit. T approaching infinity. Because I'm just going to keep writing this. Limit T approaches infinity. I replace the infinity with the T. I pump that up by 1 and divide by that number. Crank it up. Increase that by 1 power. What's negative 1/3 plus 1?
2/3.
2/3?
2/3.
Okay. X to the 2/3. Now you got to divide by 2/3, which means
Multiply by 3 halves.
multiply by 3/2. Very good. Was that okay with that? All right, limit T approach. I got to write this again. Eventually, I'm just substituting infinity for that X, right? The only thing tedious, this section's cool, but the only thing tedious, if I keep writing this, limit T approaches infinity, limit T approaches infinity. Even if I plug in a T into 1, I gotta write it for both of them. All right, limit T approaches infinity of 3/2 X to the 2/3 minus limit as T approaches infinity of 3/2 times 1 to the 2/3, which is just 1, right? I'll do the easy part first. That's just 3/2, right? So it all comes down to this. Well, that isn't like the 1/x or the 1/x squared or the 1/x cubed, is it? X to the 2/3. If you're stumbling upon how to get that limit, remember we can look at something like graphically. We can look at this graphically, but we can look at this numerically, can't we? You want to just numerically plug in numbers that are really big and see what's happening to them? So this means the cube root of a number squared. So hey, I start with 1. The cube root of 1 is 1. You square it, you get 1, right? But how about like 1,000? I mean, the cube root of 1,000, isn't that 10? But 10 squared is what? 100. So it went from a 1, I increased it to 1,000. This value right here, I used x equal to 1,000. This came out to be 100 times 3/2. Do you agree it's just going to keep getting bigger and bigger and bigger? Did anyone see this? I just used 2 numbers numerically to plug into this, just to get an idea of what's going on with this expression. This would be very similar to the graph of y equals square root of x. Because I'm like, you plug in a 1, I get 1 times 3/2, 3/2. I substitute a gigantic number, not too big, but 1,000. 1,000, the cube root of 1,000 is 10, but then 10 squared is 100. So when I plug in 1,000, I get 3/2 times 100. Still a very big number, right?
That variable is supposed to be a T.
This right here, it will be when we substitute the T. Very good, so I'm going to put that right now. When we do this limit, you're saying you're just substituting a T there. And then you're like, what goes on with that expression? Very good. So I'm like, what's the limit as T goes infinity? And like he said, make that a T. Yeah, because the T went here first, so you're right. I'm going to put that T there. Sort of like, where's the T go? But everyone, do you agree this is going towards infinity? I did, but just plugging in a couple numbers numerically to get a sense of that. At x equal to 1, it was 2 3/2. I plug in 1,000, it still jumped up to 1. A very large number. You can keep increasing this T value, this number keeps increasing. But I did that numerically. Could you even look at this graph? Angie, looking at the graph? I'm just curious. Anybody want to look at that graph? We're familiar with like y equals square root of x, right? But you're not, that's not a common function that comes up all the time. Y equal to 2/3. X to the 2/3. And you look at it. So what's the answer? This what? Diverges. Cool. Hey, anybody notice a pattern on these so far? What happened with, what's that power? Okay, and what happened? It diverged? This one diverged. What was the power here?
To the 1/3.
To the 1/3. And then 2 made this thing do what?
Converge.
Am I stumbling upon something? I know we're looking for patterns, but both of these diverged. But this converged. It's when that power down there in the denominator of x is greater than a what? 1. Y'all see that? Y'all notice that? This power right here is greater than the what? 1. This power is lower than a 1 in the denominator. But I'm being honest, you can definitely see a pattern to this. You're like, oh, okay, so what do you think would happen to the integral of 1 over x cubed? It would convert, yeah, you can play around with it. But what about 1 over, ready? I'll put it in this section. How about the square root of x? And let's say I should put limits on these, because I didn't put limits here. We'll do 1 to infinity for all these. I don't want to use 0, because that's giving us another what? That's something else we'd have to deal with in terms of the improper intervals. But how about this one right here? What's that power? 1/2, that's lower than a 1, and what's happening? It's divergent, right? So all these, we're saying that this power here, x to the 1/3, x to the 1, x to the 1/2, if that power was 1 or lower, what happened? It diverges. But if it's higher than 1, just go a little bit higher than 1, like 1.1. All right, but what do you think would happen, everyone, if I did, in terms of these problems? That's x to the 1/3 power. But what if we had the integral of 1 over x to the 3/2? Right? 3/2 is higher than a 1. 1, do you agree? So I'll put that up here. How about the integral of 1 over x to the 3/2, 1 to infinity? I mean, you do all the math, but you notice it does what? It does converge. So isn't that cool? Even at the end of this course, we do these series. Have anybody heard other students who took Calc 2 and they kind of, series. They're not bad at all, but boy does this come into play again. So remember this section. This is really helpful when we do a series. You'll come back to these improper integrals and you'll remember this. You go, oh yeah, wasn't there some kind of pattern with this 1 over x to, just call it 1 over x to the p? 1 over x to the p, if I went from 1 to infinity, dx, and what is it? If p is some value 1 or lower, what happened? It diverged. But what if the p-value was greater than a 1? Like a 1.5, or a 2, or a 3, or a 4, or 5, or 6, or 7, we found that it was actually what? Converged. Cool. It's cool when you can see patterns of that, and you can work the problem out. It's like, well, what do I expect? Just be careful.
So in a problem, like how the directions say, find out which one's convergent and divergent, only evaluate the ones that are convergent. If we see a problem that the denominator has a power lower than 1, we don't even need, we can just kind of don't even mess
Yeah, leave me a note about that, And you can mention that, as you discovered with these problems, that you noticed that would diverge. If you wanted to do that, that's fine. Like, you still show the antiderivative, but you can talk about that. Yeah, thank you. Hey, now this problem is a little bit more complicated. We'll show all the work on this one, but absolutely with that. Because we just saw that, right? And what if these were 5s, or 6s, or 8s in the numerator? You're just pulling the 8 out here, you get the same answers, But hey, the only thing with converging, we do have to find what it converges to. But I'm with you, because if you know it's divergent, like what? I'll give you an example. I'm going to use a power lower than what? 1/5? Right, Dad? That's lower than 1, right? So this thing's definitely going to diverge here. You can mention it. This is going to diverge. But, you get this problem. Here, I'll put a 3 in top. X to the 3rd. We'll work out the math to see what it's converging to. Because this will converge. I love it. Excellent. I like when you see these patterns. All right, let's try this one. All right, they got a 0 to infinity. X over x squared plus 9 squared dx. Well, I can't tell what the heck's going on here. I don't know if this is converging or if this is diverging. I went the integral from 0 to infinity. It's an improper integral. My big challenge, I'll put the limit as t approaches infinity. My big challenge is finding that antiderivative. So let's look back at all our old techniques. Partial fractions, integration by parts, or U sub. What do you think? Good. I mean, you might have been thinking partial fractions. See that denominator with the x squared plus 9, the x squared plus 9? But I'm hearing U sub, and you're correct. What would you let U equal to? Look for the higher power.
X squared plus 9.
Very good. Only the x squared plus 9. Don't use too much when you do your U sub. So when we've got this problem, we're definitely gonna do a u sub. We'll let u equal to just the x squared plus 9, and we'll say bye-bye to that x dx, while everything in terms of du. Alright, so I'll start out, I see it's an improper integral. I'll write my limit as t approaches infinity, 0 to a t. Just to start it out, but to evaluate this integral, we do need a u sub. So I'll go off to the side, let u equal x squared plus 9, but nothing else. The worst is when you I'll let u equal x squared plus 9 squared, and then this gets really complicated. No, this is all we need. So what's du? 2x dx. I want to knock out the x dx, so let's divide that 2 on both sides. So you get a lot of u subs in Calc 2 and Calc 3. Connor?
Do we have to change the bound to t, or if we leave it in the form of that, like, consider it all?
You know, I don't get upset. Other people might get upset. Connor, you got a really good question. People actually, every time I teach this section, I get a little tired of writing what every time. This lim t approaches infinity, lim t approaches infinity. In the end, all you're doing is substituting for that variable. When you get it down to here, you're substituting, you're thinking about what's happening with that expression as it goes towards infinity. Most important to me is you understand it is a limit problem, and you got to think of the graph, or think of it numerically, or apply like L'Hopital's rule or something, or some algebraic method to find that limit. I'm actually okay with that. I know others might get mad because you didn't write this lim t goes infinity. I'll write it every time, but I'm alright if you don't. You know, if you're just like, hey, infinity, and you keep getting down to here, you get this antiderivative, you know, I'll put infinity there and think of the limit on that expression. I totally understand that. Okay. So what's this now become? All this turns into a half du. I'll put this out here, 1/2. Limit as t approaches infinity. This is only a 1 up here. This is a u squared. Was everybody hear that? U went in here, but that squared still stays. This got replaced with that u. Yeah, everyone's all right with this? Hey, we'll keep working this out, but I'm curious. 1 over u squared. Before we saw this did what? When it went towards infinity, it actually converged, didn't it? Let's see. Perhaps this thing's converging. I know we have other things involved, like I have to put that back in there. But it's like, I recall this thing actually converged when we dealt with that. All right, so far so good. I have it blank here, and that's okay. And when eventually I'm going to resubstitute and put the limits back. What's the integral of 1 over u squared? That's u to a -2. What's the integral of u to -2? I should write it first. That's a u to the -2. So you don't think it's a, I know, it looks like a natural log, but it isn't. All right, so I'll write that over here. Limit as t